Welcome to Lionhearted Academy. This is Richard Tai. Today we're continuing our topics in trigonometry. Today we are starting a new topic that's very much related to trigonometry. Sine, cosine, and everything else, they are very much connected. It's called vectors. Now, what is a vector? Okay, vector is a quantity, okay, that has both magnitude and direction. Okay, so vectors is a quantity that has both magnitude and direction. So there are two concepts here for vectors. We have magnitude and we have direction. Magnitude is kind of like the value, the strength, or the absolute value. There are several ways to look at this. Is how big or how small the quantity is. And direction is, just like this says, direction is determined by angle. So that's therefore vectors has several aspects that's related to sine, cosine, and tangent because it relates to an angle here. And examples of vectors can be something like a force, like velocity, acceleration, okay, where they have both magnitude and directions. And so it's also called the directed line segment. There are several ways to represent this. So how do we represent a vector? Okay, so how representation of vectors. Let's go ahead and write it down. So representations of vectors. Now there are several ways to represent vectors. They're graphically and algebraically. Okay, so let's take a look at graphically. Alright, so in order to have a vector on the plane, okay, in the plane, so we're talking about two-dimensional vector. Okay, so it can be anything like this. It can be a simple directional it has a starting point, it has a finishing point, the initial point, it has a terminal point, and it has a direction. And it can be something like that. You can have any point as your initial point, any point as your final point. Okay, so any of those can be examples of a vector. All right, so let's call this point P. The initial point is called the initial point, and let's call this point Q. Right, let me erase this one so we don't get confused. Okay. Q can be that it's called the terminal point, is where it stops. So P is the point. P is the point where the vector value starts, and Q is where the vector ends. So this, and then this vector represents the direction represented by the direction going from P to Q, and the value is the magnitude represented by the distance between P and Q. So this will be called a vector PQ. So when we do vector, we use the initial point and then the final point, and then we use the arrow on top to indicate it is a vector. So it's called vector PQ. Okay, so this is one way to represent vectors using points in a plane. So vector V, or vector PQ, and we can give this vector a name called vector V. Okay, so we can use PQ, right, using initial points and the terminal point, or we can use a name, a letter, usually V or U, to represent this. Okay, now there's another way to represent PQ algebraically, is we use the difference between the order pair. Okay, you will use a component form to represent PQ. For example, let's say P here is, let's say, -1, 2, and let's say Q here, okay, the value of P is -1, 2, okay, and let's say the value of the order pair of Q is, let's do 4, 5. Alright, so we can represent this, let me go ahead and write it a little bit clear. -1, 2 here. So P is -1, 2, Q is 4, 5. So to represent PQ using algebraic notations, using component form, we can go ahead represent this by the X component and Y component. Now how do I get the X component? How do I get the Y component? Now notice I'm using an arrow bracket. Well, the X component is going to be the difference between the X values, 4 minus -1. So this is going to be, let me erase that, 4 minus -1, and then the Y component is going to be 5 minus 2. 5 minus 2. So in this case, our PQ vector can be written as 5, 3. Okay, so it has an X component of 5 and Y component of 3. So this is called the component form. Okay, component form of a vector. So if I say vector V is equal to PQ is equal to 5, 3, so I can also say vector V is equal to 5, 3. And then I can also use another way to represent the 5 and 3 is I can say that this is my component V1 and V2. So sometimes we also use V1 V2 instead of X and Y to represent the components. Okay, and now what do you need to know about a vector? Okay, we need to know its magnitude, and we need to know its direction. The magnitude, okay, of a vector, we represent using a double line. Double line, kind of like F's value, but it's double instead of single line. Single line bracket is a double line bracket. Double line bracket of vector V. So the magnitude is simply the distance from the initial point to the terminal point. Okay, so how do you calculate the distance? Well, the distance is the, if you remember the distance formula, it's kind of like the Pythagorean theorem, because this is the hypotenuse. If you draw a triangle, right triangle, you would have the legs here, right? And this is the hypotenuse. So it would be the x squared, x2 minus x1 squared, and then y2 minus y1 squared, and the square root of that. So here, if we already have the component, okay, well, we have to simply just take the square root of the component squared, v1 squared plus v2 squared. Now v1 would be the x component, v2 would be the y component. So in this example of ours, our magnitude of v, the magnitude of v would be square root of 5 squared plus 3 squared. Okay, because the initial point is -1, 2, the terminal point is 4, 5. So the difference between x is 5, so it's 4 minus -1 squared plus 5 minus 2 squared. Okay, that's where we get the 5 and 3 from. Alright, so this would be 25 plus 9, so it would be square root of 34. Alright, so vector V has a magnitude of 34 because that's the distance. That's how, what's the size? If you can consider that, that's the size of the vector V. Okay, alright, so that's one of the things. First important thing is we need to know how to represent the vectors using component forms, and how to find the directional, how to find the magnitude, and we need to know how to find the directional angle also. But we'll go ahead and talk about that in a little bit. Okay. So now vectors can be anywhere on the order pair on the coordinate plane, but we also have a standard position. Okay, standard position, and using a component form we have a standard position. So let's go ahead and talk about the standard position of a vector. What is the standard position of a vector? Is when the initial point is on the origin. Okay, when the initial position is on the origin. Okay, now the one thing about vector is I can move vectors anywhere I want them to, and that they would still be the same vector. Okay, let me illustrate to you what I mean by that. So let's say I have a vector. Actually, I can go ahead and draw it like this. So I have a vector like this. Okay, let's call this vector v. Now, vector v has initial point here, terminal point here, and it has a certain magnitude and direction. Now, if I move this here, the initial point and terminal point changes. But notice that the magnitude and the direction remains the same because I didn't rotate it, so it's still pointing in the same direction. Now, if I move it here, it will still be the same vector. If I move it here, it will still be the same vector. The magnitude and direction doesn't change. The only thing that distinguishes a vector from another vector is its magnitude and direction. So that means every vector that we have, we can always move them to this something called the standard position, where the initial point now becomes what? The origin. Okay, now it's 0, 0 is where's the initial point, and then we have a final point called v1, v2. So this is where we got the v1, v2 the component form from. So the basic component form of a vector with initial point at the origin okay. So it's this v equal to v1, v2. Okay, so v1, v2, because this point would be v1, this point would be v2. Now, if they give you more than 2 points, if they give you 2 points, it's very simple. If they give you 2 points, let's say p, the initial point, is equal to p1, p2, right? And then q, the terminal point, equal to q1, q2. Okay, then how do you find the initial? How do you find v? Then vector pq would simply be p1 minus q1 for the x component, and p2 minus q2 for the y component, and this can be set equal to v1, v2, and equal to v. Okay. So the magnitude is very simple. Again, the magnitude I already wrote up there. It's just using the Pythagorean theorem. It will be v1 squared, square root of v1 squared plus v2 squared. Okay. All right. Now, if the magnitude is equal to 1, then v would be you consider a unit vector, because the vector is 1 unit. And if the vector magnitude is equal to 0, then it's a 0 vector. Okay. So we'll be talking about unit vector a little bit more, but let me just write it down for now. The unit vector, vector v, the magnitude of v equal to 1, and the 0 vector like this has a magnitude of 0. Okay, the magnitude is equal to 0. And any two vectors are equal only if they have the same magnitude and directional angle. That means their component has to be the same. Okay, their component has to be the same. The v1 and v2 has to be the same. Alright, so let's go ahead and try an example here. Let's try example 1 here. Let's say we have a vector with p initial point for -7, and q has initial point, terminal point -1, 5. So let's go ahead and write this vector in component form. So vector pq would be equal to this. It would be 4 minus -1, -7 minus 5. Okay, so the component form would be 5, -12. 5, -12. All right. So let's go ahead and set this equal to v equal to 5, -12. And so we can find the absolute value, or the magnitude, not the absolute value, but the absolute magnitude of this vector. So we do the component square plus the x component square plus y component square. So square root of 25 plus 144 That's 169, square root of 169, so which is 13. So the magnitude of this vector would be equal to 13. Okay. All right. So now we haven't talked about the angles. We'll talk about the angles, directional angles, in a minute. But before we do that, let us go ahead. Let's go ahead and move on to some basic vector operations first. Vector operations. Now, some of the basic vector operations that we need to know is there are scalar multiplication, okay, vector addition and subtraction. Addition and subtraction is they're all together, because we'll talk about that, vector addition and the scalar multiplication. Okay, scalar multiplication. So let's see if we can get through these two topics today. So, how do we add vectors? Or actually, let's go ahead and do a scalar multiplication first. Okay. Now, what do I mean by scalar multiplication? What is a scalar? Now, if you say scalar is just a number, then you're right. Scalar comes from the word scale. Okay, scalar is just a constant, a numerical constant, a number. Okay, so when we do scalar multiplication, what we're saying is we're just multiplying the vector by a number. Okay, we're just multiplying the vector by a number. So for example, if v is equal to 4, 3, okay, let's say v is equal to 4, 3. So let me go ahead and draw it just to show you. Okay, so if v is 4, 3, 1, 2, 3, 4, 1, 2, 3. So it has 4 as x component and 3 as the z component. So let's go ahead and draw it like this. So 4, 3, alright. Okay. Yep. Oh no. Probably want to put a point here. So 4, 3. So let's go ahead. Oops. I undid that. Alright. So let's say this is 4, 3, right? Okay. So this is v. 4, 3. Alright. So what does 2v mean? Well, 2v means twice of the vector. Okay. 2 times the vector v, which means twice. So when you do scalar, this is a scalar, this is a constant, multiplied by this, you multiply all the component by the scalar. So 2 times 4 is 8, and 2 times 3 is 6. So 2v would be 8, 6. As the x component of 8 and the y component of 6. It's basically the same vector. Okay, let me use red. It's the same vector, however, you can say it's what? Twice the length. So this is v and this is 2v. You can see that it has the same directional angle, right? It's on top of each other, it's the same directional angle, but it's twice as long as v. So that's why it's called 2v. And if you do 3v, you just simply multiply everything, all the components by 3, so it's 12 and 9. Okay, and you can do 1/2 v. 1/2 v would be equal to 2 and 3/2, right? 3 divided by 2. And you can even do negative v. What does negative v mean? Well, negative v means you do -4 and -3 because we multiply all the components by negative. Now let's take a look at what does negative v look like. So it will be -4, 1, 2, 3, 4, and then 1, 2, 3. So -3, -4, this point, terminal point would be here. So it would be, let me go ahead and use a different color. Let me use blue here. It will be here. So negative v, okay, is a little not very perfect. It's the exact same vector of v, but in the opposite direction. You see, it's going in the opposite direction. So whenever you multiply a negative number by a negative scalar by a vector, you're basically turning it around. And if you multiply by different numbers, either you make it larger or you can make it smaller. So that's the basic concept for scalar multiplication. Okay, basic concept of scalar multiplication. All right. Now, What about now? Let's talk about what about when you add vector addition. So let's say we have vector u, which is u1, u2, and then we want to vector v, v1, v2. Well, there are several ways to add. Let me show you graphically, and let me show you algebraically. Okay. So graphically, okay, let's just go ahead and do two vectors. All right. I'm just going to use blue here. All right. So let's say this is vector u. And let's say this is vector v. Okay, so this is u, this is v. So how do I add them together? Okay, now graphically we have something called the parallelogram law. Okay, we can use the parallelogram rule to add vector v and u together. What do I mean by that? Okay, well, to add vector u and v together, okay, let's say we do u plus v. So what I do is I move v. Okay, hold on, I'm not in the right. I move v and then put the initial side of v by the terminal side of u. So I move v. Okay, I move v to connect up to u like this. So when I do u plus v, what I will do is then I will go ahead and draw a vector from the initial side of initial point of view to the terminal point of v. So this vector in red will be u plus v. Okay, it will be u plus v. So basically that's how you add. So that's why graphically it's very easy to add u plus v. Okay, and now u plus v and v plus u will be the same. So we can show you why it would be the same. But graphically this is how you go ahead and do it. You take the second vector that you want to add to the first vector, you put it on the terminal side, and then you go ahead and do this, and then this comes out to be u plus v. Now algebraically, how do we add? Well, algebraically, what do we do is we add the components. As you can see, this distance originally was u1, u2, right? I mean, this point was u1, u2 from here. The difference is u1, u2 from here. The difference is v1, v2. So basically, we're adding all of them together. So we add u1 plus v1, and then we add u2 plus v2. Okay. So this is how algebraically how we add vectors. It's very simple. You just add their components together. That's all you have to do, add their components together. And when you multiply a scalar, you just simply multiply the scalar into the components, right? So when you multiply a scalar by k times u, you will simply just be k times u1 and then k times u2. So those are the rules for vector addition, and this is scalar multiplication. Alright. So u plus v. Now let me show you why u plus v is the same as v plus u. So as you can see, this is u plus v, right? Alright, now let me go ahead and do this, and I can show you. So if I copy this, okay, and I go ahead and move it here, alright, oops, I didn't really copy it. Alright, so now I have, okay, I'm going to leave the v here. So as you can see, this is u plus v. So I'm going to move v to the initial point of view, and I'm going to copy u, and I'm going to move u, okay, the initial point u to the terminal point of v, and then look at this. This would be v, right? The green is v and the blue is u. So if I do v plus u, I will have the same result as u plus v. So this is a property that will work, okay, that will work for vector operations, which is u plus v equal to v plus u. So let's take a look at some of the properties of vector operations. Okay, let's take a look at vector operations. Now, what about u minus v? Okay, if I want to do u minus v, before I do the look at the operations, let me show you what does u minus v look like. Well, to do u minus v, let's go ahead and copy this again. All right, so this is u, right? Now, if I want to do minus v, Now remember, what does negative v look like? Negative v look like this, but instead of going this way, negative v is going that way. So hold on, let me go ahead and put u here. Let me go ahead and give myself a little bit more room. So this is u, and this is v, right? But okay, if I do this, if I do u here and v here, right? But if I, instead of put the initial point of v at the terminal point of u, I put the initial point here, I put it backwards, because this would be negative v. Okay, so ignore this. This would be negative v. I'm doing v, but I'm going this direction. Okay, so that's negative v. And then if I want to add them together, I go ahead and use that parallelogram method again. Okay, connect the initial point of u all the way to the terminal point of negative v. So this would be u minus v. Okay, that would be u minus v. Alright, now how do I do it algebraically when you do u minus v? Well, it's very simple. You just do u1 minus v1 for the x component, and u2 minus v2 for the y component. Okay, so let me show you an example. Alright, let's say vector v is -2 and 5, and then vector w is equal to 3 and 4. Alright, so what would 2v be like? 2v would be, you just multiply simply the scalar 2 times the v, would be -4 and 10, because you take 2 times -2 is 4, -4, 2 times 5 is 10. Okay, now what would w minus v look like? Well, you simply take w minus v, this is 3 minus -2 for the x component, and 4 minus 5 for the y component. So this would become 5, -1. Okay, 5, -1. It's very simple. Now what about 2v minus 3w? Okay, what would that look like? Well, let's go ahead and do 2v first. Well, we already got 2v, so it's -4, 10. Alright, and what about 3w? Okay, so it's 3 times w, 3 times 3 is 9, 3 times 4 is 12. Then you subtract them. Okay, so it will be -4 minus 9 is -13, 10 minus 12 is -2. So that would be 2v minus 3w. Okay, so algebraically is very simple, and you can also do this graphically when you go ahead and use graphical representations, and that's not going to be too much trouble to do graphical representations. Alright, so let me go ahead, let's go ahead and talk about one more thing for today. Okay, one more thing for today is, let's just finish this with properties, since we already talked about operations. Properties of vector addition and scalar multiplication. Okay, so that once we understand the property, we can go ahead and do this without much problem, and we can know the rules. It's always important to remember these properties, and a lot of properties are a carryover from properties that we already learned from before, like commutative property. Okay, so first, u plus v is equal to v plus u. So I have demonstrated that that's true. This is a commutative property of vector addition. Now, then we have the associative property of vector addition. So u plus v plus w is equal to u plus v plus w. So I can switch the association between the addition components. I can add u plus v first, or I can add v plus u first. Okay, either way, if it's addition, it will not change. Now vector u plus vector 0 is still vector u. That's the identity property for addition, identity property for vector 0. Vector u plus the opposite of vector u should give us vector 0. Okay, that's the identity property, I believe. And then we have scalar. Okay, c. Okay, now notice, if I go ahead and if I don't put a vector sign on it, it means scalar. Okay, so c times d times u is equal to c times d times u. So this is an associative property of scalar multiplication. And then we have distributive property of scalar multiplication. So if I do c plus d times u, I can do c times u plus d times u, and then I can do scalar multiplication. This is another distributive property. Okay, if I do scalar times u plus v, I can do cu plus cv. Alright, so it's distributive property. Now identity property, if I do 1, then number 1 times vector u is of course equal to itself, u, okay, and then 0, if I do a 0 number, now notice it's not a 0 vector, okay, 0 times vector u will be a 0 vector, okay, 0 vector and the 0 scalar are different, alright, and the magnitude of CV, the magnitude of C times vector V would be the absolute value of C times the magnitude of V. Okay, this is the absolute value. Alright, so we'll be using these properties in the lessons to come. And the next lesson we'll be talking about a little bit more about vectors, like unit vectors and directional angles and things like that. And so we'll carry on the discussions in our next lesson. If you have any questions or comments, please leave them in the question and comment sections. And then we hope to see you again in our next lesson. Thank you.